So we're Eltham College. I'm Olesh Chaban.
I'm Ethan Southard.
I'm Ben.
I'm Artav Gupta.
Alice Anderson.
The world is looking to become more sustainable, and carbon emissions from transport are becoming a larger concern for many. This has led to the introduction of measures such as the ultra-low emission zone in the UK. Bikes have always been a staple of sustainability, and now, with the added electrical capacity, they become a practical mode of transportation for many. Using our models, we seek to predict the growth of e-bike sales, the factors causing this growth, and the wider spread impact that e-bikes will have.
For the first problem, we were tasked with predicting the number of e-bike sales in the US in the years 2025 and 2028. Our first assumption was that there'll be no significant change in the rate of development of e-bike technology, as this would be difficult to predict accurately. We also assumed that any member of the population who already owns a working bike or e-bike won't buy another bike until there's brakes, as most members of the population have no need for more than one bike. Given that most parts of both standard and electric bikes can be replaced, excluding the frame, which lasts for about 10 years, we take 10 years to be the standard lifetime of any bike. To simplify the model, we chose to assume a constant population, and we only modelled 15 to 64-year-olds, as those under 15 aren't allowed to ride an e-bike without adult supervision in some parts of the US. And those over 64 are less likely to need e-bikes, especially given they're unlikely to need them for commuting. We also assume that due to the early stage of the e-bike market, most e-bike sales are due to the influence of others with e-bikes. And finally, we assume a homogeneous mixing of those with and without e-bikes.
As per our assumption that the influence of others is a primary motivator for e-bike sales, we decided to use an adapted SIR model. We used 3 different states: those with bikes, those with e-bikes, and those with neither. Note that there's no direct transition from the bike state to the e-bike state. Instead, we assume a member of the population moves via the non-cyclist state. Our sales of e-bikes is proportional to both the non-cyclist and e-bike population to approximate the word-of-mouth spread. Here, alpha is our infection rate, and we remove e-bikes at a rate of 1 over their lifespan. Conventional bike sales are proportional only to the non-cyclist population, since it's a well-developed market that doesn't require word-of-mouth spread. We also remove conventional bikes at a rate of 1 over their lifespan. Finally, we ensure that the rate of change of the population is 0. To use this model, we need to find the initial values of each population. After plotting e-bike sales across the last 4 years, we found that an exponential regression suitably modeled the data in the short term. We would not expect this trend to continue indefinitely, since exponential curves are unbounded. However, it serves as a likely approximation across the previous 10 years. We integrate under this curve to find our initial e-bike population. Since we assume that e-bikes last for an average of 10 years, there's no need to go prior to 2012. Using an approximation of the number of conventional bike owners from online sources, we can now find our non-cyclist population. And recalling that alpha times m times e gives us our e-bike sales, we can rearrange the equation to find our infection rate. We can use a similar tactic to find gamma. Using ODE45, a function provided by MATLAB, we can solve the system numerically across the next 10 years. ODE45 is ideal for this task since it provides a good trade-off between accuracy and efficiency when applied to non-stiff problems.
This graph shows the projected population sizes over the next 10 years. There is a nonlinear increase in the e-bike population and a leveling off of the conventional bike population as expected. Our overall predicted sales for 2025 were around 1.33 million and 1.76 million in 2028. Some strength of our model is that we accounted for word-of-mouth spread instead of just regressing on the given data to provide more accurate results. Our results were also realistic, as research after the competition found that our results were similar to professional predictions. However, our model does not fully show the effect e-bikes will have on conventional bike sales, since we assume a word-of-mouth spread. Instead, we assume that the bike population, the bike sales, is a constant proportion of the people without any bikes. Our model is also invalid once mainstream, since we assume word-of-mouth spread. If bike companies substantially invest in conventional marketing strategies, then word-of-mouth spread becomes less important. We should also consider people who will never buy a bike due to location, disability, or other factors.
For this problem, we were asked to determine the relative importance of different factors on the sales of e-bikes. We considered the factors gas price, battery price, disposable income, environmental awareness, and urban population. We firstly assumed that a data set is representative of trends between samples, and that the data varies approximately linearly between each recorded value. Furthermore, it is necessary to assume that if a factor is considered important via the random forest algorithm, it is also a factor that is causing these sales. To model relative importance, we used a random forest algorithm which predicts e-bike sales given data on the considered factors. We will explain how this algorithm works by first explaining how a regression tree works. A regression tree is a mechanism by which you predict a target variable via a series of decisions. It is a type of decision tree that outputs a continuous variable. To produce the tree, a number of possible binary splits are attempted on the training data set, each with a different condition. For each possible partitioning, the impurity is calculated. Impurity is a measure of diversity in the output variable. In our case, we used mean squared error of the predicted variable. The split that reduces the impurity the most is selected. This process continues recursively until criteria to control the tree growth has been met. A single regression tree may overfit the training data set, so instead many regression trees are used. A technique called bagging is implemented to avoid the trees from becoming too similar. To do this, the data set is split into many sub-data sets of selected records and features. Each data set is then used to produce a single regression tree, which may be different to the others in the forest. When test values are entered, each tree outputs a prediction value. The final prediction is the average of all the predictions from the forest. In a decision tree, at each node, impurity values are calculated. We use mean decrease in impurity as a measure of feature importance. To calculate this, for partitions on a given variable, find the change in impurity between parent and child nodes weighted by the number of samples that they split. We repeat this across all the splits on the variable in the tree to find the total decrease in impurity, which is then averaged across the forest. If a variable is useful, it will reduce the impurity by a lot. Hence, variables with a high mean decrease in impurity are highly connected to the output variable. This is a suitable measure of feature importance via the random forest.
When we first ran the model, relative environmental concerns scored extremely low importance, which may have been due to the fact that we were considering the 4 possible survey responses as 4 individual factors. To overcome this, we decided to calculate a consolidated value for relative environmental concern each year, which we did by calculating a weighted sum, for example, multiplying the proportion of people who cared a great deal about the environment by 1, and those who cared a fair amount by 0.67. Our initial runs of the model worked, but we found it was prone to varying outputs each time we ran it, and that the dataset was too small to generate accurate predictions for e-bike users each year. To generate more data, we therefore decided to use piecewise linear interpolation, which we believe to be valid given our assumption that the data we had encapsulates all major trends. A small minority of the factors were also missing data from either the years 2012 or 2022, so we performed linear extrapolation on these factors to ensure we could still use the full 10 years of data. This slide shows the code that we used to perform the linear interpolation. It was first important to clean the data, identifying and removing all nan values. We then used the optional inbuilt extrapolation mode in the MATLAB linear interpolation library, which allowed us to easily extend the data for the full 10 years where necessary. After consolidating the environmental data and collating the interpolated data onto a spreadsheet in MATLAB, we split the data into training and testing datasets. Then, using the training dataset and the Python scikit-learn library, we created a random forest regression model and found the percentage error using the testing dataset. We were able to find the relative factor importance for each of the factors, and we iterated this process 100 times using a different training and testing dataset for each random forest. We then took the average feature importance for each of the factors across all of the forests.
Using our improved model, we found that disposable income was the most important factor. This seems reasonable given the elevated cost of e-bikes. Next was urban population, followed by battery price, gas price, and finally environmental awareness. It also seems reasonable that environmental awareness is the least important factor, since the most environmentally aware consumers will choose even more eco-friendly modes of transport that avoid producing e-waste. The outcomes of our model are justifiable, as previously outlined, and by using a random forest regression rather than a single tree, it should be robust against overfitting. Additionally, we achieved a high R-squared of greater than 0.99. Whilst this is to be expected, given our use of linear interpolation, it does indicate that the model can accurately predict e-bike sales across our testing dataset. Unfortunately, we were unable to find data that directly dealt with e-bike cost, so instead used battery price as a proxy. Additionally, we didn't consider as many factors as we would have liked, and the model can fall victim to correlation fallacy. just because a factor closely follows the trends in e-bike sales does not necessarily mean that it's causing the e-bike sales.
In this problem, we were asked to quantitatively model the impact e-bikes will have on traffic congestion and carbon emissions. Our assumptions were that purchased e-bikes will be used for every commute. We assume that all e-bike owners commute, since there's a large motivation for buying e-bikes, and everyone in a model is between 15 and 64, so is of commuting age. E-bike purchases are distributed between commuter groups, excluding existing cyclists. Limited data exists on how current modes of transport affect e-bike sales. Next, we assume that bikes and e-bikes do not contribute to congestion, as any contribution to congestion would be minimal. Road networks have a constant maximum throughput of cars per minute. This keeps our model independent of specific road networks, as different maximum throughputs can be used. Congestion only affects urban areas, and all e-bikes are bought in urban areas. From our second model, urban population was a very significant factor in e-bike sales, so we can assume that the vast majority of them are used in urban areas. Finally, we assume carbon emissions are proportional to commute time. This allows us to disregard the differences in emissions of idle and moving vehicles, which we could not model using the data available. Additionally, we assume that carbon emissions for all cars is the same, and this will not change over the next 10 years.